And now in this lecture we'll find out the length of chord CB. In the drawing we have a semicircle. We know that the center of this semicircle is at this point, point O. Inside this semicircle we have square DEOF. This is a square, and we know that the area of this square is equal to 5 square units, and our mission is to find out the length of this chord CB. So first of all, because of the fact that DEFO is a square, we know that all the angles inside the square are right angles. So those two angles are equal to 90 degrees. Those two angles are also equal to 90 degrees. Those two angles are also equal to 90 degrees. Okay? And we also know that the area of this square is equal to 5 square units. So here, if we have L square this square ABCD could be any square. We'll define one side of this square as x, that is to say it is equal to x units in its length. Therefore, because of the fact that all the sides of a square are equal to each other, all the other sides must be also equal to x. So the area of this square ABCD, that could be any square, will be equal to x times x. X times x is x squared. So we found out the general formula for the area of any square. It is equal to x squared, when x is the length of one side of the square. Okay. The next step, I will copy our square in this new page, and we will find out the length of one side of our square. So this is square DEFO that are coming from the original drawing. We will define one side of this square as x. Therefore, the other side must be also equal to x, because of the fact that all the sides of any square are equal to each other. So the area, it is given us the question that the area of square DEFO, the squared brackets is the sign for the area. It is equal to 5 units according to what is given us the question from one side. But from the other side, the area of square DEFO, it is equal to x squared. According to this formula, the area equals to x squared. Okay? So we know that the area equals to 5 square units, and it is also equals to x squared. Okay, therefore we know that for one side the area of square DEFO equals to 5 square units. From the other side the area equals to x squared. Okay, so we can find out the equation that 5 equals to x squared. We will take a root out of this equation, and we will get that x equals to the square root of 5 units. So we found out that one side of square DEFO equals to the square root of 5 units. Okay, in the next step we'll join points D and O together by a straight line. By joining points D and O, we actually created the right green triangle DOF. So we will implement the Pythagoras theorem on this right green triangle DOF. So I'll copy the right green triangle in the new page and we will implement on it the Pythagoras theorem. So actually, this is the right triangle DFO that I copied from the original drawing. Here, by PT is the abbreviation for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars in any right triangle. The hypotenuse here is DO, therefore the square of the hypotenuse is DO square, and it must be equal to the sum of the squares of the perpendiculars, that is to say, it must be equal to DF square plus FO square. That is to say, DO square must be equal to df square. df equals to the square root of 5, therefore df square equals to the square root of 5 square plus fo square. fo equals to the square root of 5, therefore fo square equals to the square root of 5 square. So in conclusion, we found out that do square equals to the square root of 5 is 5 plus square root of 5 is 5. So do square equals to 5 plus 5, that is 10. Here we'll take a root out of this equation and we will get that do equals to the square root of 10 units. So we found out that the length of the hypotenuse do equals to the square root of 10 units. Here it is equal to the square root of 10 units. But do starts from point O, that is the center of the semicircle, and ends at point D, that is a point on the circle itself, a point on the semicircle itself. This is exactly the definition of a radius. So we can write down that DO is the radius of the semicircle it is equal to the square root of 10 units. So we know that the radius of the semicircle equals to the square root of 10 units. What is the definition of OB? My segment OB starts from point O, that is the center of the semicircle, and ends at point B, that is the point of the semicircle itself. This is exactly the definition of a radius. That is to say, OB is the radius of the semicircle, that is equal to the square root of 10 units. Likewise, if we focus on line segment OA, it starts from point O, that is the center of the semicircle, and ends at point A, that is the point on the semicircle itself. Therefore, OA is the radius of the semicircle, that is equal to the square root of 10 units. In the next step, I will present to you rule number 1, and we will implement rule number 1 in our drawing. According to rule number 1, the sum of the angles on one side of a straight line is equal to 180 degrees. So if we have the straight line AB, we choose any point on this straight line. For example, we choose point K, and we have here side KL. And according to this rule number 1, the sum of the angles on one side of the straight line is equal to 180 degrees. So here we have the upper side of the straight line AB, and we have the lower side of the straight line AB. if you focus on the upper side of the straight line AB at point K, the sum of the angles must be equal to 180 degrees according to this rule, rule number 1. So which angles we have at the upper side of AB? The straight line AB, we have angle AKL, this angle, plus angle BKL. That is to say, the sum of those two angles AKL plus BKL must be equal to 180 degrees according to this rule, rule number 1. The same thing is true about the lower side. The sum of the angles on the lower side of the straight line AB must be equal to 180 degrees. So if you focus on the lower side of the straight line AB here at point K, the sum of the angles must be equal to 180 degrees. That is to say, this angle is equal to 180 degrees. Because of the fact that it is a straight line, it is obvious that it is equal to 180 degrees. We can say that angle BKA is equal to 180 degrees. It is a straight line, therefore it is obvious that it is equal to 180 degrees. Okay, now we can implement rule number 1 in our drawing. Okay, we know that this is a semicircle and AB is always the diameter of the semicircle. AB is the diameter, as the diameter of the semicircle, it is absolutely a straight line. Okay, so we can write down that AB is a straight line. So if we focus at the upper side of the straight line AB at point O, the sum of the angles must be equal to 180 degrees according to rule number 1. So which angles we have at the upper side of AB at point O? We have one angle that is equal to 90 degrees plus the missing angle that is actually angle EOB. In total, the sum of those two angles must be equal to 180 degrees according to rule number 1. I'll repeat again. If we focus at the upper side of the straight line AB at point O, there the sum of the angles must be equal to 180 degrees. Which angles we have at the upper side of AB at point O? We have 90 degrees plus the missing angle EOB. In total, they must be equal to 180 degrees according to rule number 1. Here we will subtract 90 degrees from this equation, and we get that the missing angle EOB equals to 180 degrees minus 90 degrees, it is equal to 90 degrees. So the missing angle is the right angle. This angle, it is a right angle. That is to say, it is equal to 90 degrees. And because of the fact that angle EOB is a right angle, it means that the pink triangle EOB is a right angle. So we can implement the Pythagoras theorem on this pink right triangle EOB. So we copy the pink right triangle in a new page and we implement on it the Pythagoras theorem. So actually, this is the right triangle EOB that I copied from the original drawing. Here by PT is the progression from Pythagoras theorem. We'll implement here the Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in this right triangle EOB is EB, therefore the square of the hypotenuse is EB squared. And it must be equal to the sum of the squares of the perpendiculars, that is to say it must be equal to EO squared plus OB squared. Okay. So EB squared, that is the square of the hypotenuse, must be equal to EO squared. EO equals to the square root of 5, therefore EO squared equals to the square root of 5 squared plus OB squared. OB equals to the square root of 10, therefore OB squared equals to the square root of 10 squared. In conclusion, we found out that EB squared equals to the square root of 5 squared, that is 5 of course, plus square root of 10 squared, it is 10. So EB squared equals to 5 plus 10 is 15. Found out that the length of the hypotenuse is equal to the square root of 15 units. Our mission is to find out the length of this chord called CB. We have already found out that EB equals to the square root of 15 units. The only thing that is left to find in order to find out the length of CB is to find out the length of line segment CE. In order to find out the length of line segment CE, we will make a construction. We will complete first of all the semicircle to a circle. So first of all, we completed the semicircle to a circle. And in the next step, we'll extend line segment EO on both sides. That is to say, we'll extend line segment OE towards the upper side, of the circle until it touches the circle, and we will define the touching point of the extended line segment OE and the circle as point M. In the next step, we will extend line segment EO towards the lower side of the circle, and we will define the touching point of the extended line segment EO and the circle as point N. So what is the definition of ON? O is the center of the circle, N is the point on the circle itself, therefore ON is the radius of the circle that is equal to the square root of 10 units. And what is the length of line segment EN? From the drawing it is very easy to see that EN equals to EO plus ON. Again, EN equals to EO plus ON. So EN equals to EO, that is square root of 5, plus ON, that is square root of 10. In conclusion, we found out that En equals to the square root of 10 plus square root of 5. The length of line segment En equals to the square root of 10 plus square root of 5 units. What is the length of line segment ME? From the drawing it is very easy to see that ME equals to MO minus EO. I'll repeat again, ME equals to MO minus EO. From here, ME equals to ME equals to MO minus EO. So ME equals to MO. O is the center of the circle, M is the point of the circle itself, therefore MO is the radius of the circle, that is equal to the square root of 10 units, minus EO. EO equals to the square root of 5 units. In conclusion, we found out that ME equals to the square root of 10 minus square root of 5. In the next step, I will present to you rule number 2, and we will implement rule number 2 in our drawing. According to rule number 2, rule number 2 is true in any circle. So in any circle, if chord AB, this is chord AB, this is chord AB, intersects with chord CD, this is chord CD, it's point O. Again, chord AB intersects with chord CD, it's point O. Point O is the intersection point of the two chords. So, if you have two chords that intersect with each other, then the following equation is true, that that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. Okay, AO times OB equals to CO times OD. We actually can implement rule number 2 in our drawing. Why? Because in our drawing we have chord MN. This is chord MN. This intersects with chord CB. This is chord CB at point E. Point E is the intersection point between the two chords. Therefore, we can implement here rule number 2. So I'll copy the two chords, the new page, the two chords that intersect with each other. Chord MN passes through the center of the circle, this is to say from point O. So here we have chord MN. This is chord MN. This passes from the center of the circle. It intersects with chord CB. This is chord CB. And the intersection point occurs at point E. Therefore, so I write it down. In our original drawing, chord MN intersects with chord CB at point O, at point E. This is the point of intersection. We have already found out that ME equals to the square root of 10 minus square root of 5, and E equals to the square root of 10 plus square root of 5, and finally EB equals to the square root of 15. Therefore, according to rule number 2, we will get that ME times EN equals to CE times EB. CE times EB. Again, because of the fact that chord MN is accessed before CB at point E, therefore ME times EN equals to CE times EB. ME, we will substitute ME by square root of 10 minus square root of 5. We will substitute EN by square root of 10 plus square root of 5. CE is the missing line segment, so we leave it as it is, times EB. EB equals to the square root of 15 units, so we substitute EB by square root of 15. According to the algebraic identity that A times B equals to B times A, we can change the order of those two expressions. And we can write down that square root of 10 plus square root of 5 times square root of 10 minus square root of 5 equals to CE times square root of 15. According to the algebraic identity that A plus B times A minus B equals to A squared minus B squared, we will get that our expression square root of 10 plus square root of 5 times square root of 10 minus square root of 5, it is, according to this algebraic identity, is equal to A squared minus B squared. In our specific expression, A equals to the square root of 10 and B equals to the square root of 5. Repeat again, in our specific expression, A equals to the square root of 10 and B equals to the square root of 5. Why? Because we have square root of 10 plus square root of 5 times square root of 10 minus square root of 5. You can see it easily that A equals to the square root of 10 and B equals to the square root of 5. And according to the algebraic identity, A plus B times A minus B equals to A squared minus B squared. That is to say, this expression equals to A squared. A equals to the square root of 10. A squared equals to the square root of 10 squared. That is 10 minus B squared. B equals to square root of 5. Therefore, B squared equals to the square root of 5 squared. That is to say, it is minus 5. So in conclusion, we found out that this expression equals to 10 minus 5. 10 minus 5 is 5. According to rule number 2, this expression equals to CE times square root of 15. Is equals to CE times square root of 15. Here we will divide this expression by square root of 15, and we'll get that CE equals to 5 over square root of 15. So the missing line segment here, it is equal to 5 over square root of 15. And what is the value of the chord that we are looking for? The value of chord CB. It is very easy to see from the domain that CB equals to CE plus EB. I'll write it down. The length of the line segment that we are looking for, chord we are looking for, CB, it is equal to CE plus EB. I'll repeat again. CB equals to CE plus EB. That is to say, CB equals to CE. We just right now found out that CB equals to 5 over square root of 15 plus EB. EB equals to square root of 15. So in conclusion, we found out that the length of the chord that we are looking for, chord CB, it is equal in total to 5 over square root of 15 plus square root of 15. And this is actually the answer to our question. But here we'll simplify this expression because we don't want that in the denominator we will have a square root. We want to eliminate the square root in the denominator of this number. So in order to eliminate the square root in the denominator, we multiply square root of 15 by square root of 15, and then we divide it by square root of 15. So it is 5 over square root of 15, and then we multiply square root of 15 by square root of 15, and then we divide it by square root of 15. So square root of 15 over square root of 15 is 1, so we multiplied square root of 15 by 1, so we change nothing. So it is allowable to do it. So we found out that CB equals to 5 over square root of 15 plus square root of 15 times square root of 15. That is to say, CB equals to 5 plus square root of 15 times square root of 15 is 15 over square root of 15. That is to say, CB equals to 5 plus 15 is 20 over square root of 15. Again, we have a square root in the denominator, so we want to eliminate the square root in the denominator. Therefore, we'll multiply this expression CB, that is equal to 20 over square root of 15. We will multiply it by square root of 15, and then we will divide it by square root of 15. We multiply it by 1, so we change nothing. Therefore, it is allowable to do this operation. So in conclusion, we get that CB equals to 20 times square root of 15 over square root of 15 times square root of 15 is 15. Here we will divide both the numerator and the denominator of this expression by 5. And we get that CB equals to 20 over 5 is 4. So in total in the numerator we have 4 times square root of 15 over 15 over 5 is 3. So in conclusion, we found out that the length of this chord CB, the chord that we are looking for, it is either equals to 4 times square root of 15 over 3 units, or in terms of numbers, it is equal to 5.164 units. Repeat again, the length of chord CV, this chord, it is equal to either 4 times square root of 15 over 3 square units, over 3 units, or in terms of numbers, it is equal to 5.164 units. So in the next step, I will summarize the lecture. So, in the original drawing, we have here a semicircle. We know that the center of this semicircle is at this point, point O. Inside the semicircle, we have this square DEFO, and we know that the area of this square is equal to 5 square units, and our mission is to find out the length of this chord called CB. So first of all, we know that all the angles inside any square are right angles. So those 4 angles, they are all right angles. And we know that the area of this square DEFO, it is equal to 5 square units. So here we have, I drew here square ABCD that could be any square. We defined the length of one side of this square ABCD as x. What is the area of this square ABCD? This equals to x times x. That is to say, the area of square ABCD equals to x times x, that is x squared. So we have a formula for the area of any square. Why? Because ABCD could be any square. So the area of square ABCD, the area, the square bracket is the sign for the area, equals to x squared. So actually we can use this formula in order to find out the length of one side of our square DEFO. So I copied square DEFO from the original drawing. This is square DEFO, and we defined one side of this square, the length of one side of square DEFO, it is equal to x units. Therefore, all the sides are equal to x because of the fact that all the sides of any square are equal to each other. So for one side, we know that the area of square DEFO it is equal to 5 square units according to what is given as the question. From the other side, we have the general formula for any square. According to the general formula, the area of our specific square DEFO must be equal to x squared. Okay, again, from one side, the area of the square is 5 square units. From the other side, it is equal to x squared. Therefore, x squared equals to 5. We took out of this equation and found out that x equals to the square root of 5 units. So here, all the sides of square DEFO are equal to 5 square units in their maps. And then we joined points D and O together by a straight line. By joining points D and O, we created here the right green triangle DFO. So actually can we implement the Pythagoras theorem on this right green triangle. So I copied the right green triangle DFO in a new page here, and we implemented the Pythagoras theorem on this right triangle DFO. We have already found out that side DF equals to the square root of 5 units. Side FO also equals to the square root of 5 units. The only missing side is the side of the hypotenuse, DO. According to the, here by PT is the version for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The square of the hypotenuse is DO, therefore the hypotenuse is DO, therefore the square of the hypotenuse is the O square, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to df square plus fo square. So do square, that is the square of the hypotenuse, must be equal to df square. df equals to square root of 5, therefore df square equals to the square root of 5 square plus fo square. Fo square equals to the square root of 5, therefore fo square equals to the square root of 5 square. So in conclusion, we found out that do square equals to the square root of 5 is 5 plus square root of 5 is 5. In conclusion, we found out that do square equals to 5 plus 5 is 10. Here we took root out of this equation and found out that do equals to the square root of 10 units. So the hypotenuse do equals to the square root of 10 units. But here, because of the fact that point O is the center of the semicircle. Point O is the point of the semicircle itself. This is exactly the definition of a radius. That is to say, DO, that is equal to the square root of 10 units. It is the radius of the semicircle. DO is the radius of the semicircle that is equal to the square root of 10 units. So we know that the radius of the semicircle is equal to square root of 10 units in its length. So here, OB, what is OB? O is the center of the circle, B is the point of the circle itself, therefore OB is the radius of the semicircle that is equal to the square root of 10 units. Likewise, in line segment AO, point O is the center of the semicircle, point A is the point of the semicircle itself, therefore OA is the radius of the semicircle that is equal to the square root of 10 units. Then I presented to you rule number 1, and we implemented rule number 1 in our drawing. According to rule number 1, the sum of the angles on one side of a straight line is equal to 180 degrees. So here AB is a straight line. We choose any point in the straight line AB. For example, we choose point K, and here we have side KL. if we focus on the upper side of the straight line AB here, at point K, the sum of the angles must be equal to 180 degrees according to this rule, rule number 1. So which angles we have at the upper side of AB at point K? We have this angle, that is angle AKL, plus this angle, that is angle LKB, or BKL, it is the same. So angle AKL plus BKL, in total, they must be equal, the sum of those two angles must be equal to 180 degrees according to this rule, rule number 1. The same thing is true about the lower side. The sum of the angles in the lower side of a straight line is equal to 180 degrees. That is to say, if we focus on the lower side of the straight line AB here, at point K, the sum of the angles must be equal to 180 degrees. That is to say, this angle, angle BKL, is a right angle, it is equal to 90 degrees. And because of the fact that BKL is a straight line, BKA is a straight line, it is obvious that angle BKA equals to 180 degrees. So we can implement rule number 1 in our drawing. Why? Because in our drawing we have the semicircle, we have this semicircle, we have this semicircle, and we know that AB is the diameter of the semicircle. AB is the diameter of the semicircle, it is absolutely a straight line. Okay? So, actually, if we focus on the straight line AB at point O, and on the upper side of the straight line AB at point O, again, AB is the diameter of the semicircle, it is a straight line. So if we focus on at the upper side of the straight line AB at point O, the sum of the angles according to rule number 1 must be equal to 180 degrees. So which angles we have at the upper side of AB at point O? We have this angle that is a right angle, it is one angle of out of 4 angles of the square, that is right angle, it is equal to 90 degrees, plus the missing angle, that is actually angle EOB. In total, the sum of those two angles must be equal to 180 degrees according to rule number 1. 90 degrees plus angle EOB must be equal to 180 degrees according to rule number 1. Here we subtracted 90 degrees from this equation and found out that the missing angle EOB must be equals to 180 degrees minus 90 degrees, it is 90 degrees. So the missing angle EOB is a right angle, it is equal to 90 degrees. If angle EOB equals to 90 degrees, it means that the pink triangle EOB is a right triangle. Therefore, we can implement the Pythagoras theorem on the right pink triangle EOB. So I copied the right pink triangle in a new page, and we implemented the Pythagoras theorem on the right pink triangle EOB. This is the right triangle EOB that I copied from the original drawing. We know that EO equals to the square root of 5 units, OB equals to the square root of 10 units. The only missing side is the hypotenuse EB. By PT is a proportion from Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is EB, therefore the square of the hypotenuse is EB squared, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to EO squared plus OB squared. So EB squared must be equal to EO squared. EO equals to the square root of 5, therefore EO squared equals to the square root of 5 squared. Plus OB squared. OB equals to the square root of 10, therefore OB squared must be equal to square root of 10 squared. So EB squared equals to square root of 5 squared is 5, plus square root of 10 squared is 10. In conclusion, we found out that EB squared equals to 5 plus 10, that is 15. That is to say, EB squared equals to 15. We took a root out of this equation and found out that EB equals to the square root of 15 units. Yeah, the square root EB, the hypotenuse AB equals to the square root of 15 units. And here also EB equals to the square root of 15 units. Okay, our mission is to find out the length of chord CB. This is called CB. We've already found out that EB equals to the square root of 15 units. The only thing that is left to find in order to find out the length of CB is to find out the length of line segment CE. In order to find out the length of this line segment CE, we completed the semicircle to a circle, and then we extended side OE on both sides, in the upper side and in the lower side. We extended side OE or line segment OE towards the upper side of the circle until it touches the circle at point M. We extended line segment EO towards the lower side of the circle until it touches the circle at point N. ON is the radius of the circle because it starts from the center of the circle and ends at point N, that is the point on the circle itself. Therefore, ON is the radius of the circle, it is equal to the square root of 10 units. And EN equals to EO plus ON. EN equals to EO plus ON. That is to say, EN equals to EO, that is equal to 5 units, plus ON, that is the radius of the circle and the semicircle, that is equal to the square root of 10 units. In conclusion, we found out that EN equals to the square root of 10 units plus square root of 5 units. What is the length of line segment ME? The length of line segment ME, it is equal to MO minus EO. Again, ME equals to MO minus EO. ME equals to MO minus EO. MO is the radius of the circle. Why? Because it starts from the center of the circle, that is to say from point O, and that's at point M, this is the point on the circle itself. This is exactly the definition of a radius. Therefore, MO is the radius of the circle, that is equal to the square root of 10 units. And EO, it is equal to the square root of 5 units. So in conclusion, ME, that is equal to MO minus EO, it is equal to the square root of 10 minus square root of 5. Here, ME equals to the square root of 10 minus square root of 5. And we already found out that EN equals to the square root of 10 plus square root of 5, and EB equals to the square root of 15 units. In the next step, I presented to you rule number 2, and we implemented rule number 2 in our drawing. According to rule number 2, in any circle, if chord AB intersects with chord CD, if chord AB, this is chord AB, that intersects with this chord CD at point O, the intersection point between the two chords occurs at point O. So if this is the situation, then according to this rule number 2, we will get that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. Okay, we can implement rule number 2 in our drawing. Why? Because in our drawing we have chord MN that passes from the center of the circle and intersects with chord CB at point E. Chord MN intersects with chord CB at point E. So I copied the two chords that intersect with each other on the new page, and we implemented rule number 2 in our drawing. Here, chord MN that passes from the center of the circle intersects with chord CB. This is chord CB. So chord MN intersects with chord CB at point E. Point E is the intersection point between the two chords. Therefore, according to rule number 2, we get that ME times EN equals to CE times EB. Again, ME times EN equals to CE times EB. We have already found out that ME equals to the square root of 10 minus square root of 5, EN equals to the square root of 10 plus square root of 5, and EB equals to the square root of 15. The only missing line segment is line segment CE. Okay, so we substituted ME by square root of 10 minus square root of 5. We substituted EN by square root of 10 plus square root of 5. And then CE is the missing line segment, so we leave it as it is, and EB equals to the square root of 15, so we substitute EB by square root of 15. Okay. Then we have the algebraic identity that A times B equals to B times A. That is to say, we can substitute or we can change the order of those two expressions. Okay, we did it and we got that square root of 10 plus square root of 5 times square root of 10 minus square root of 5 equals, according to rule number 2, to CE times square root of 15. Then we have the trigonometric identity that a plus b times a minus b equals to a squared minus b squared. Okay? And here, in our specific expression, that is to say square root of 10 plus square root of 5 times square root of 10 minus square root of 5, a equals to the square root of 10 and b equals to the square root of 5. Okay? And according to the algebraic identity, this expression that is a plus b times a minus b equals to a squared minus b squared. That is to say, this expression equals to a squared minus b squared, according to our trigonometric identity. But we already found out that a equals to square root of 10, therefore a squared equals to 10. We already found out that b equals to square root of 5, therefore b squared equals to 5. Therefore a squared minus b squared will be equal to 10 minus 5. In conclusion, we found out that the value of this expression equals to 10 minus 5, that is 5. So we found out that this expression that is equal to 5 equals to CE times square root of 15 according to rule number 2. Here we divided this expression by square root of 15 and we found out that CE equals to 5 over square root of 15. Here CE, the missing line segment, equals to 5 over square root of 15. And what is the length of chord CB, the chord that we are looking for? CB equals to CE plus EB. Again, CB equals to CE plus EB. I'll repeat again. CB equals to CE plus EB. That is to say, CB equals to CE, that is equal to 5 over square root of 15, plus EB, that is equal to square root of 15. So the answer to our question is that the length of chord CB, the chord that we are looking for, the length of this chord, it is equal to 5 over square root of 15 plus square root of 15. Here we simplified this expression in order to eliminate the square root in the denominator here. We actually multiplied square root of 15 by square root of 15 and then we divided by square root of 15. In this way we found the common factor in this expression, that is square root of 15. So CB equals to 5 over square root of 15. Again, we multiplied square root of 15 by square root of 15, and then we divided by square root of 15. So we multiplied by square root by 1, so we change nothing. Therefore, it is allowable to do the operation. So CB equals to 5 plus square root of 15 plus square root of 15 times square root of 15 is 15 over square root of 15. In conclusion, we found out that CB equals to 5 plus 15 is 20 over square root of 15. Again, we want to eliminate the square root in the denominator, therefore we will multiply this expression by square root of 15 and then we will divide it by square root of 15. Again, we multiply this expression 20 over square root of 15. We multiply it by square root of 15 and then we divide it by square root of 15. And we found out that CB equals to 20 times square root of 15, and square root of 15 times square root of 15 is 15. So in conclusion, we found out that CB equals to 20 times square root of 15 over 15. Here we divided both the numerator and the denominator of this expression by 5, and we found out that CB equals to 20 over 5 is 4. So in total, in the numerator, we have 4 times square root of 15, and 15 over 5 is 3. So in the denominator in total we have 3. In conclusion, we found out that the length of this chord called CB, it is equal to either 4 times square root of 15 over 3 units, or in terms of numbers, it is equal to 5.164 units. Okay, thank you very much.